I'm Ken Cordova, and I'm an electrical engineering student.
I'm Jacob Woolman, and I'm a chemical engineering student.
I'm Justin Crump, and I'm a mechanical engineering student.
I'm Rob Rodriguez, and I'm an aeronautical engineering student. And we are
The Benson Burners.
Sparkyville's booming population means that they have ever-changing energy needs, and in order to meet those needs, they require a system that can be placed anywhere, anytime they need it. To meet these needs, they need a system that provides clean energy that's affordable and reliable and can fit in with its environments without negatively impacting their daily lives. Some of the key parameters for this project include that it does not taint Sparkyville's clear air and that it fits within any potential lots that it could be needed.
Our design is a structure made of 1x2-inch wood beams. It includes a modular solar panel top that is adjusted at a 45-degree angle for maximum light absorption. It's lightweight and stable, won't tip over, and we don't have to worry about spillage from water because it's strictly solar panels. I made an estimated budget materials spreadsheet. It includes all the materials we need to complete our project. If this goes as planned, our project should end up costing about $33.
To find power from voltage, we need to use the equation voltage squared divided by the resistance, which in this case is 100 ohms. This gives us a power in some unit of watts. We need to multiply that by 1,000 to equal however many milliwatts. With one of our solar panels, we make 0.3 volts. 0.3 volts squared times 10 equals 0.9 milliwatts. Now this would sound like we need a lot of solar panels to make 50 milliwatts, but since the equation is exponential, it's not as many as you think. So to find out how many solar panels we need, we plug in 50 milliwatts divided by 10, which is the number we multiply voltage squared by. We then get voltage squared equals 5. So we square root everything, and that means we only need 2.23 volts to equal 50 milliwatts. If each solar panel makes 0.3 volts, we divide 2.23 by 0.3, which means we need around 7.4 solar panels, or 8 solar panels. Some scientific principles related to our design included circuits and how we wired each solar panel individually to collect the voltages and move them towards the output. Another one included the photovoltaic effect, which is when sunlight loosens an electron from its bond and makes it travel down a wire, which is how solar panels work basically. Another is the relationship between voltage, resistance, and power, which is how we discovered how much voltage we needed to make 50 milliwatts. And our last scientific principle was about triangles and how we used the Pythagorean theorem to discover many different angles and lengths through what we needed to build.
Now, let's look at how renewable energy is currently being used in the United States. Of total energy used, about 12.2% is from renewable sources. About 46% of that is from hydroelectric, about 39% is from wind, and 6% is from solar. Now that might look as if one is objectively better than the other because it is used more, but it actually comes down to situational components. For example, let's look at each individually. Let's look at wind. An industrial wind turbine weighs in the neighborhood of 176 tons. That means every time the turbine would need to be moved, millions of dollars would have to be spent on specialized drivers and reinforced trucks. Not to mention the fact that the turbine itself costs well over $1 million. The only truly efficient use of wind turbines comes when many can be used in a normally windy area. In Sparkyville, however, much of the wind will be diminished due to the surrounding buildings, and the wind turbines will be an incredible eyesore to surrounding communities. Not to mention, actually anchoring the wind turbine to a lot will cause incredible damage when it is eventually removed. Now look at hydroelectric power. Most hydroelectric power is produced in large quantities from structures such as the Hoover Dam, not small water wheels. A water wheel the size and weight that is necessary to produce large quantities of power that Sparkyville needs would be even more difficult to transport than wind turbines and requires access to moving water in order to work. We live in a desert. That access to moving water is rare and may be unreliable. Hydroelectric power may not even be truly renewable. For example, California no longer considers large hydroelectric structures to produce renewable energy because of the damage they cause to waterways, as well as the migratory patterns of certain fish. Solar really is the only option for this project. When solar panels are scaled up, they grow wider, not higher. They are modular, and a solar farm can be broken down into much smaller parts. In Sparkyville, nearly 300 days out of the year have sunlight. In fact, there are already companies that create mobile solar panels for personal and commercial use. Because of the versatility of solar panels, our design can be used not only for Sparkyville's needs, but for disaster relief across the South and Southwest.
Even though solar is the best idea in the real world, we still have yet to figure out if it works just as well on a smaller scale. So we created a decision matrix to decide which design we wanted the best. As you can see here, we have Idea 1, Idea 2, and Idea 3. Idea 1 works with both solar power and water power. Idea 2 is only water power, and Idea 3 is only solar power. As you can see, the most important criteria that we chose was power, fragility, and realism. As you can see, with all the scores added up together, Idea 3 won out just by a little bit over both solar and water. We used this decision matrix to decide on which design we were going to go with in the end, and we are very pleased with our results so far.